I'm doing my research in dynamical systems, and in particular in differentiable dynamical systems in a small dimension. Generally speaking, as long as there is something that moves, I'm interested in what we can say about the property of the system. So what is its long-time behavior? Could we find out that there is some richness of the dynamics, so lots of different dynamical phenomena that arise, or on the contrary, is there some kind of rigidity, or something that prevents dynamical phenomena to appear? And I'm interested in different kind of such systems. So starting from, for example, what are called web flows in dimension 3. So they are particular systems, but they are well studied. There is a wide literature on it because there are some famous examples like geodesic flows on surfaces are for Riemannian metrics are example of web flows, and so they motivate a lot the study of such systems. But also on the other side, for example, you have Beltrami vector fields, who are also other examples of kind of web flows. So Beltrami vector fields are particular solutions, stationary solution of the Euler equation. So you see it appear in the study of the dynamics of fluids, of perfect fluids. And also some other examples that I'm very interested in are billiards, for example. When you study billiards dynamics, so the systems is quite easy to describe. So you just take some domain in our tool. I like to do like convex domains, but there are plenty of different families of billiards, and you just do what you would do like in a bar with friends. So we just take a ball, let's say that it's massless, and you put somewhere on the boundary of your table, and you just have to shoot your small ball. So you have to, once you decided where to put yourself on the boundary of the table, you just select some direction along which, so same angle along which you want to shoot your small ball. And then once this is fixed, then your ball follow like a straight line inside the table, and until at some point it will meet again the boundary of the table, and over there it will reflect. And standard billiards, so in the conservative case, what happens is that the angle of incidence must be equal to the angle of reflection. And then, so you have another point, new points on the boundary, a new velocity direction, and so you can start to redo the same scheme again. And so it's just you are defining just a dynamical system. So you are defining some maps that you could iterate again and again. And so these maps turns out to be conservative. So there is some area that is preserved. So what I described is something that is called Birkhoff billiards. And so it was introduced by George Birkhoff in the 30s. But actually, fun fact, the really first person was thinking about playing billiards inside some circular domain actually was Lewis Carroll. So I'm interested, I will try during the colloquium to say something about what we can say in this case. So in particular, when you start in the rigid framework of analytic billiards, so when you assume that the boundary of your table could be described from an analytic function, so that adds a lot of rigidity, but we can see that there is still a lot of richness of the dynamics. You can change a little bit the rules of the game, and you can add some dissipation. So dissipation is a phenomenon that try to describe like you had some friction, and so it's quite natural to try to add it to in the study of dynamical systems that whose aim is try to describe like the real world, because we have friction, and so we have to deal with it. And in the case of billiards, how you can do this? I was talking about the angle of reflection when you shoot your ball. And instead of asking that the angle of reflection is equal to the angle of incidence, you ask that when you bounce, you lose a little bit of the angle. So when you bounce, the new direction becomes bends towards the normals a little bit. That could be translated by saying that there is the tangent component of the velocity vector becomes a little bit smaller. And then again you have like new points, a new velocity that is a little bit modified, and you go again, you continue to apply your systems, and what happens is that then there is no more area that is preserved, and you make it appear something that are called attractors. because you will have something that looks like one-dimensional invariant sets that will attract all the points of your phase space where you are defining your dynamics. And in that case, it's interesting to try to understand, okay, which kind of attractor do they have? Are they simple? Are they complicated? And I will try to explain that during the colloquium that actually you can have both for billiard tables, depending on the strength of the dissipation and so on and so forth. So there is a huge case that could be described, and that for me are really interesting. So during my stay here in CRM and in Barcelona, I'm mostly collaborating with Immaculada, Baldomà and Tere Martínez-Seara from UPC. We have an ongoing project about billiards in the analytic setting, and so in particular our aim is trying to show that some dynamical property that is called the Kupka-Smale property is generic among analytic billiards, and a more long-term aim would be to prove that you have what is called universality inside analytic billiards. That is what I mean by universality, is showing that if you take like an analytic billiard, you can make it appear as some first return map up to a small error, any diffeomorphism of the disk. So you have plenty of dynamical phenomena that appear, and the aim would be to realize it inside the more rigid framework of the analytic setting. And beside that, I would like also to start to discuss. We have some good perspective, let's say, and some good starting point to discuss also with Eva Miranda, who is also at CRM and UPC, and with her we would like to more focus about still these questions about universality, but more within web flows and within some, in particular, some kind of solution of the Euler equation. When you want to do research in maths, you need time, you need to be patient. And the fact is that, okay, sure, there are like plenty of possibility of communicating online, like Zoom meetings or email and whatever. But the fact is that the positive things of being able to stay here for whole months is that like you can discuss like with the people one day, and then you go back and then you think of it, and then the next day you come and then you have new ideas. And doing research in maths is something that takes time, and it's something that you cannot just say, okay, I will do like, we will solve these problems in 1 hour during a Zoom meeting or in 3 days of staying. So it's really the fact that you can really enjoy a longer exchange with people that really allows you to fully enjoy like the exchange with other researcher on a long time. It's undeniable that there is a problem in about the presence, or maybe the not presence of women in the field of mathematics, and so in particular in pure mathematics. So I think that my opinion is that some programs like the one of CRM Chair of Excellence like are extremely important also for like showing to also PhD students and master students that there are women doing maths. For me, it was really important. Like for example, my master thesis advisor was a woman, and one of my PhD advisor was a woman, and for me that was really important because I know that okay, there are women doing maths and doing like good maths, and they can enjoy, and there is no reason why women should not do and go for doing research in maths if they love it.